This mini lecture will cover chemical bonding as well as trends in the periodic table. I would like to show you this example first, which has to do with sulfur. Sulfur was used in history as a component of a warfare agent, such as in this picture of a Greek fire. This happened when sulfur was first discovered. Sulfur is also called brimstone, and it is a lemon-colored stone. It will sort of burn in a very peculiar way. It looks almost like liquid fire. But what it does is it emits noxious fumes, and that is why it was so effective as a weapon. Let me first start out by talking about the most important topics that you will have to focus in on in your book. The electron configuration and the periodic table properties. Get familiar with effective nuclear charge and the periodic trends in properties of the elements. Also, you have to learn how to do the electronic configuration of ions, not just elements, but also when the elements are charged. Furthermore, you must learn about the ionic radius as well as the periodic trends of all the main group elements. This is the periodic table of all the elements that are known to date. What I would like to do is give an illustration and just focus in on 6 elements and demonstrate the periodic trends on this excerpt of carbon, nitrogen, oxygen, silicon, phosphor, and sulfur. So what I have done on this slide is basically summarize the PowerPoint presentation that has been provided to you by McGraw-Hill Education and summarized a multitude of slides into just one slide in which all of the periodic trends are summarized. So in going from left to right in the periodic table, or in this small excerpt that I have taken out of the periodic table, these 4 trends are increasing from left to right, including electron affinity, electronegativity, ionization energy, with some exceptions, and the effective nuclear charge. Contrary to that, a decrease occurs from left to right in the atomic radius and the metallic character. That's why I colored these 2 arrows in red. As you move from the top to the bottom, the metallic character increases as well as the atomic radius. And similarly to down here, the decrease from top to bottom is in ionization energy and electronegativity. So if you can sort of keep this entire picture straight in your mind, you will be able to solve a lot of problems that have to do with elements and the periodic table trends. Now let's focus in on electronic configuration of ions. In the last module, you have already learned electronic configurations of regular elements. But now what happens if an atom loses an electron or gains an electron? When an atom loses an electron, such as sodium in this example, then it becomes a positively charged cation, sodium plus. And it is this outermost electron in the S shell that is being lost. And that S shell is now not here anymore. So what you do is you write the entire electronic configuration without the S electron. Now, the opposite occurs when an electron is added. So in chlorine, for example, this is the electron configuration of chlorine element. But now if an electron gets added, the electron gets added right here in the empty p orbital that only is occupied with 5 electrons and now has 6. Now, if this is too long and too tedious for you to write, you can also use the abbreviated version with a noble gas core. So you can just use the noble gas core and then notate just the outermost valence electron. Here is a summary of all the chemical bonding and its related topics to chemical bonding. There are 2 types of bonding, the ionic bonding and the covalent bonding. In an ionic bonding, an entire electron gets transferred from one atom to another. An example is sodium chloride. Sodium loses its electron and transfers it over to the chloride. In covalent bonding, however, the electrons are shared, such as diatomic hydrogen. These two electrons in here belong equally to each hydrogen. Now, with ionic structures as well as covalent bond structures, you have to learn what's called the Lewis dot structures in both the ionic bonding and the covalent bonding. And with the Lewis dot structures also comes a phenomenon called resonance. And this resonance is basically the delocalization of charge in an atom or a molecule. And as you're drawing these Lewis dot structures and draw the resonance phenomena, you must also at all times obey the octet rule. The octet rule has only a few exceptions. So, with these concepts in mind, we also have to take a good look at one periodic table trend that you have learned, and that is the electronegativity. Because electronegativity, or the love for electrons, has a direct implication on whether a molecule is polar or not polar. So, let's have a look again at sodium chloride. Sodium is on the very left-hand side of the periodic table, while chlorine is pretty far to the right. So that means that chlorine is a lot more electronegative than sodium. That means that the dipole moment is directed towards the chlorine. So there is a net dipole moment. On the other hand side, hydrogen and hydrogen have both equal amount of electronegativities. So that means that the dipole moment is net zero, because the dipole moment going from here to here or from here to here cancel each other out. Another example of a net dipole moment not being zero is water. Oxygen here is a lot more electronegative than hydrogen. That is why the electron dipoles are being pulled from the hydrogen to the oxygen. That also denotes that the oxygen has a partial or delta negative charge, while the hydrogens have a delta positive, a partial positive charge. So this results in a net dipole moment, which makes water a polar molecule. On the other hand side, carbon dioxide has a zero net dipole moment, because one vector goes from the carbon to the oxygen, and it is cancelled out by the opposite vector from this carbon to this oxygen. So, let's look at an example of a Lewis structure, a resonance, and how the octet rule can be obeyed. So this is SO3. So if you draw all the Lewis structures of SO3, you will have to delocalize the electrons. Please keep in mind when you do draw the Lewis structures, as well as all resonance structures, you must pay attention to the negative formal charges. So for example, if we start out with this first Lewis dot structure, there's a negative charge on this oxygen, because there's one extra electron in its valence shell. The same thing is occurring on this oxygen. There it is negative. On the other hand side, the sulfur is 2 positive because it misses 2 electrons. So therefore, overall, the molecule SO3 is a neutral molecule. So now, when the electrons are being delocalized, what happens is that these 2 electrons get pushed into here to make a double bond, and that double bond formation then causes this double bond over here to break, and these 2 electrons are now being placed on this oxygen. And this results in this Lewis structure. Now, the negative charge that was originally on this oxygen has now been placed on this oxygen. Once again, resonance is the delocalization of charge. The sulfur still remains 2 positive, and this oxygen is negative as well. So once again, these 2 negative cancel the positive of 2 plus out. Therefore, the overall structure is neutral. So let's look at one more resonance structure. Here, this electron pair can also be pushed into this sulfur-oxygen bond to make a double bond. Oops. And that then would lead into the breaking of this double bond, and then these 2 electrons are being placed on this oxygen. Now this results of the originally negative charge here to be delocalized onto this oxygen, and this now becomes neutral. So these are the 3 resonance structures of SO3, and you also have to put a bracket around all of these resonance structures, indicating that the resonance structures are sort of going back and forth between each other, forming a resonance hybrid. So, looking at all of the atoms in SO3, sulfur, oxygen, all 3 oxygens, at all times is the octet rule obeyed, meaning that each time the atom has 8 electrons in its valence shell. So, in conclusion, why did we learn about chemical bonding and periodic table trends? Well, this knowledge allows us to predict the outcome of chemical reactions. So, a question for you is, sulfur, which is in matches, and fire creates what? Question mark.